On behalf of the Montana State University Honors College Honors Presents team, we thank you for watching Student Presents, an opportunity for students to share their interdisciplinary passions with others. Stay tuned for our next speaker, and if you are a Montana State University Honors student and are interested in giving a talk like this, please consult the description below. Enjoy!
Thank you for joining me today. My name is Greta Gustafson, and I will be discussing how diet influences methanogen activity in bovine. I would like to start with a brief overview of the presentation and what we will be discussing today. First off, why does this topic matter? I will review some data about the impact cattle have on the U.S. as a whole. I will then introduce background information regarding how much cattle contribute to methane production and how methanogens are essential to their digestive system. I will then bring in some current research on how changing the diet of cattle can possibly alter methane production. We will then go over some conclusions and recap what was discussed. My family owns and operates a cattle ranch in Montana, and this is a photograph I took of one of our own calves. So why is this important? There are 94.4 million cattle in the U.S. as of 2020. In 2018, there were 217.5 billion pounds of milk produced in the U.S., along with 26.8 billion pounds of meat produced. In 2014, there was $165 billion of the U.S. economy contributed to the cattle industry, and in 2018, there was $8.3 billion in exports contributed to the U.S. cattle industry. These values show why this topic matters. Cattle are a significant part of the world, and understanding the most environmentally friendly way to produce them is essential. As many of you know, during digestion, cattle produce methane. The main contributors of methane coming from the cattle industry are enteric fermentation, manure storage and degradation, which is when manure is processed, there are still methanogens in that sample and they can still release methane even though they are not within the rumen system any longer. And the other contributor is cropping and fertilizer practices. There are 3,740 million tons of non-CO2 emissions, meaning methane and nitrous oxide, per year globally, and 2,344 million tons of those emissions come directly from enteric fermentation of cattle. The livestock contribute to 7.3 to 7.5% of global greenhouse gas emissions and 3.1% in the US. I chose to focus specifically on cattle rather than all ruminants because they make up the majority of ruminants around the world. So how does this process work? Cattle eat plants filled with cellulose and are able to digest them with the help of methanogens. Most non-ruminants cannot do this efficiently. Methanogens are located in the rumen, shown here in red. And after food is ingested, it is broken down to products like acetate, propionate, and butyrate, which have a lot of carbon that methanogens can access. And while the methanogens can use this for their cellular processes, methane is released into the rumen and released into the environment by exhalation and eructation. Cattle are able to absorb the fatty acids, vitamins, and nutrient content that is released during this process, and without methanogens, these carbon products would not be broken down as efficiently, and cattle would not be able to utilize the nutrients. The first study I would like to introduce was done by Romero Perez and colleagues in 2015. The sustained reduction in methane production from long-term addition of 3-nitrooxypropanol to a beef cattle diet. This study took 8 cannulated heifers, and if you're unfamiliar with the term cannulated, it is when a hole is produced in the body wall of the animal, and that allows access to the rumen so you can take samples of ruminal fluid and analyze them. This study was conducted over 146 days and consisted of one control group that was fed 0 grams per day of NOP and one supplemented group that was fed 2 grams per day of NOP. The mixed feed ration consisted of barley silage, grain, calcium carbonates, canola meal, salt, urea, molasses, and vitamins. And the supplemented group had NOP mixed in directly with their feed ration. So what is 3-nitrooxypropanol, or NOP? It is a structural analog of methyl coenzyme M. Methyl coenzyme M inhibits methyl coenzyme M reductase, also known as MCR. MCR plays a role in the last step of methanogenesis. Here you can see the chemical structure of NOP. This study used 10% NOP in silicon dioxide, as pure NOP is a volatile compound that becomes less stable with increasing temperature. The formulation was effective, but researchers mentioned that it needs to be assessed under more diverse scenarios to see that it maintains stability. The first set of data points this study explored was the dry matter intake, body weight, pH, volatile fatty acids, and NH3 measurements of these animals. As you can see in the first two columns here, the dry matter intake and the body weight were consistent across the control and the NOP group. This is important because it means that the group being fed NOP ate just as much as the control group and weighed the same, meaning the NOP being included in the ration did not affect their feed intake, and both groups were still able to efficiently utilize nutrients to sustain body mass. The ruminal pH of heifers fed NOP was slightly higher, 6.64 compared to 6.44, than the control group. However, it didn't seem to have any negative effects on the animal. In this graph, you can see how pH changed over time after feeding, the control group shown in solid and the NOP supplemented group shown in dashed lines. The volatile fatty acid levels of heifers fed NOP, shown here, saw a decrease in acetate and an increase in propionate and butyrate compared to the control. NH3 levels, shown here, in NOP-fed heifers were slightly lower than the control. The next data set that the researchers explored was the rumen microbial populations of both groups. Researchers analyzed the microbial populations of the rumen contents of both control group and the NOP supplemented group by using 16S rRNA gene sequencing technology. As you can see here in this graph, the methanogens in the NOP treatment group were significantly decreased compared to the control group. However, during the recovery period, when the researchers removed NOP from the diet and both groups had the same mixed feed ration, you see that the methanogen presence starts to increase even though it has not reached the level of the control group. Researchers then looked directly at methane emissions from enteric fermentation using metabolic chambers to measure these results. In all three groups of methane emissions, methane in grams per day, methane in grams per kilogram of dry matter intake, and as a percentage of gross energy intake, you can see that the NOP group had a significant decrease in overall methane produced compared to the control group. Researchers compared their results to similar studies and concluded that feeding the NOP mixed directly into the ration resulted in significantly less production of methane than studies that had fed NOP alone or by injecting it directly into the rumen. They concluded this was because the mixed ration method allowed the NOP to be introduced gradually as animals consumed the feed, and the synchronization between the gradual delivery and feed fermentation improved the inhibitory potential of NOP. This first graph on the left shows the methane production throughout the day after the initial feeding period. As you can see in the control group, you have a significant spike in methane production after the feeding, and the NOP group does not see that spike in methane production. Both groups continue to level out throughout the day. In this bar graph on the right, you can see methane production as grams per kilogram of dry matter intake. Throughout the supplementation period, you can see the drastic difference between the control group and the NOP group of methane production. However, when you look at the recovery period where both groups did not have NOP in the diet any longer, you can see that methane production in the NOP group returned to the normal level. Another factor that the researchers think contributed to the significant reduction in methane production was the singular feeding strategy, meaning they fed only once a day. They assumed that the singular restricted feeding time increased how long the NOP was able to remain in the rumen as a result of a reduced rate of passage, allowing it to work more effectively. Overall, the researchers concluded that adding NOP reduced methane emissions per kilogram of dry matter intake by 59.2% over a 112-day period with no signs of adaptation. However, when NOP was taken away from the diet, the methane emission levels returned to normal. The second study I would like to introduce was conducted by Lee and colleagues in 2015, the effects of encapsulated nitrate on enteric methane production and nitrogen and energy utilization in beef heifers. The purpose of this study was to determine how feeding encapsulated nitrate affected methane emission and nitrogen and energy utilization. This study used 8 cannulated heifers and observed them over 4 28-day periods. They had 4 groups with 4 different diet designs, and these diets were fed once daily. The first group was a control group that contained only encapsulated urea. The second group contained 1% encapsulated nitrate. The third group contained 2% encapsulated nitrate, and the fourth group contained 3% encapsulated nitrate. All of the diets contained a mixed feed ration, and measurements were taken via ruminal fluids, feces and urine collection, and respiration chambers. So what is encapsulated nitrate? It is a complex of nitrates surrounded by oxygens, carbons, and hydrogens. It was developed because it is less toxic than pure nitrate when being added into the diet. Nitrate has to be added slowly into the diet because incomplete nitrate reduction can often lead to nitrate poisoning. You can see in these images here pure nitrate compared to encapsulated nitrate complex. The mechanism of this in its ability to reduce methane production is that it acts as a hydrogen sink in the rumen and competes with methane formation. The first data points that this study explored was the feed intake and body weight of all 4 groups. Here you see the control group, 1% EN, 2% EN, and 3% EN. As you can see in these figures, the dry matter intake remained consistent across all groups, as well as the body weight at the beginning and the end of the study. This means that the EN being supplemented within the ration did not cause the heifers to refuse feed or lose any weight throughout the study. The second data point they explored was in enteric methane production. They used respiration chambers to measure these values in grams per day and grams per kilogram of dry matter intake. As you can see, as the levels of encapsulated nitrate increase in the diet, the levels of methane production decrease. The 3% EN diet saw the most drastic decrease in methane produced by grams per day and grams per kilogram of dry matter intake compared to the control groups. This graph shows a visual of methane production hours after feeding. You can see how the control group has a peak methane production in grams per kilogram of dry matter intake right around 6 hours after the initial feeding period, compared to the 3% encapsulated nitrate group that does not have as high of a peak of methane production. This line here shows the 1% encapsulated nitrate group and the 2% encapsulated nitrate group. So this again proves that as the level of encapsulated nitrate increases in the diet, the methane production decreases. So what can we conclude from these studies? We know that cattle contribute significantly to the food supply and economy, and that they utilize methanogen metabolism to digest their food. This process produces methane and contributes to greenhouse gas emissions. However, feeding supplements in the diet can reduce methane production, especially supplements like NOP and encapsulated nitrate that are able to interfere with the methanogenesis process. These two studies only looked at the effects of feeding NOP and EN separately, but there is a lot of research going on that involves combining certain supplements in the diet and exploring other supplements that interfere with methanogenesis. More research needs to be done on the stability of these substances and how to implement them in a natural environment to ensure success. I think it would be interesting to explore further research in other ruminant species as well. If you have any questions, please contact me via D2L. Thank you for your time.